Welcome back everyone to our hands-on session on TopoToolbox. This is a continuation from yesterday's one. I'd like to hand over the mic to our instructors Dr. Wolfgang and Dr. Eugen to carry on the session.
Okay, welcome back, everybody. And so today we have quite some time, I would say, in terms of developing the code and seeing what we can do about what we have actually introduced yesterday. And so one thing that I forgot to say yesterday is that, of course, it also requires some data. And so if you open the link that I provided yesterday to you, this pad thing that didn't really work for our polling exercise, but you will find this link here now where you can download the example data that we will need. And at best, so this is a zip file. At best, you download it. You don't need, or at best, don't place it in the TopoToolbox folder, but place it somewhere else into a directory that will then be your working directory for today. Okay. So in the end, so I'm working on my remote machine here. It should look like this. Okay, so I'll show the link again. But what you should have downloaded the zip file, and once you have extracted it, there should be a folder with data, and then there are a couple of files in it. Okay, and at best, you place your working directory or just the folder in which you are could be just one above. So it's just a folder above your data. Okay, so you have your working directory. In my case, it's called CRN, cosmogenic radionuclides. Within that folder, you have your folder data, which contains all the data that you have. And we will then place the code just in that working directory. But the link, yes, here it is once again. It's up there. Yopad.eu. There you go. That's the link. Next time I'm going to create a tiny URL. That also works. MATLAB Online could be a problem, I think. It should work, but it's I'm not sure. I never tried it because MATLAB Online. I'm not sure whether it uses the max files that are part of it. It should, I don't know, I've never tried it for the MATLAB Online version because I think that MATLAB won't like that there are some max files in it. And max files are compiled C code, and it might be tricky to work with that in the online version. Otherwise, we'll see. Okay, does everybody have the link? Did you download the data? Unzip it? Half an hour. Yeah, there's, I can, a USB stick and distribute it. Now really, is it that slow? I hope. What about the others? Is it also that slow? Okay. What shall we do? I thought the connection would be much faster here. Yeah, I guess it's a problem when 50 people download at the same time. Couldn't we have such a distributed system? But as soon as some have successfully downloaded the data, then it should become a bit faster for the others. So who has successfully downloaded the data? Okay. Okay. So I think we start anyway, and what I will do so when I write the code, we can do that also together, of course, but in between I will copy and paste it into that pad. Okay, so you can then copy and paste it to your MATLAB command window or editor and then execute it as well. Okay, so I hope to be not too fast, but I can't be too slow because otherwise we wouldn't be able to finish. Okay, so I said we have two different kinds of data. The first one is, if you remember, are those basins, those shape, or this shapefile with the drainage basins for which basin-wide denudation rates have been measured. So that's what you download from the Octopus database. So what they have, it's a polygon shapefile. You could open that in any GIS, or as we will do it, we will open it in MATLAB. Okay, and there's a command that is not used or that is not part of TopoToolbox, but it's part of the mapping toolbox. That's why we need it. It's just called shape read. Okay, it reads a shapefile, and it has auto completion. So when we see here, okay, our data is in data, and then it's this one. Okay, so it's a bit modified from what we have when you would download it directly from the Octopus database. I reprojected it into another coordinate system, 4326. That's just a normal geographic coordinate system, WGS 84. They use some different Google Mercator projection that was not recognized by MATLAB, unfortunately. So when you do that, you get what is called a structure array. Okay, I hope you can see that also. It's probably fairly small, but you will see that we now have a new variable in our workspace. It's called basins, and when you double click on it, you see the contents, and you can see it's a lot of data. It's in a similar way when you open a shapefiles attribute table in a GIS, okay? So you have a geometry column saying, okay, it's all polygons that we have here. There's a bounding box. A bounding box is just a minimum enclosing rectangle. Then something that you don't see in a GIS, it's the X and Y coordinates, just listed as vectors. So the first polygon has 13,520 X coordinates and the same number of Y coordinates. And then what follows is a large bunch of numbers and data that are attributes of each of these basins. Okay, and most of this data is not of interest here for us. You can see, okay, the region, Himalaya, Nepalese Himalaya, Maziandi, so it's a kind of bit of a mixture between geographical names. You will notice that all of them are located in Nepal. That's because we have clipped that data before. And there's one particular variable that we are interested in. And where is it? It's the one that contains the 10 beryllium erosion rates. And that's this one here. So erosion based on beryllium, and the unit, I hope you can see it, is in millimeters per kilo year. Okay, so the erosion is expressed in units, millimeters per kilo year. And you can see the first entry is 180 millimeters, so 18 centimeters per 1,000 years that you would have as an erosion in each, or in the first basin. Okay? So we just need to, oh no, this is the arrow. Sorry, it's that one here. This one, it's 1,004, so it's about a meter in that case. Okay, now I also downloaded the DEM. And you see that as a TIFF, the DEM underscore GCS, that just says that it's in a geographic coordinate system, and that's about 130 megabytes. So that's the big chunk of data that the network doesn't allow us to download right now. If you wouldn't have that data, TopoToolbox would give you an access point, okay, to download that data automatically. So, if you were downloading some other extent, not the Nepalese Himalaya, but let's say for Uttarakhand or so, then you could use Toolbox to automatically download a DEM for the particular extent. For that, you will need this extent, and that's just the first exercise so that you know how to actually handle these structure arrays. Okay, so what I want to determine is, well, what's actually the extent of our shapefile? What is the left edge? What is the right edge? Upper and lower. Okay? And I do that because structure arrays have a bit of a peculiarity to work with. Okay, so when we want to determine the minimum value, we can calculate, well, we take our basins, okay, x, and then this is one of the fields, x we GS 84. And so why do I do that? Well, basins has many entries, 168. And by using those brackets, I will create a vector of all of these entries and then get, with the minimum command, I get the minimum x value. Yes. Couldn't be. It's as tight as it can be. Or is it here?
It's a loose little bit. Yeah? It's a loose little bit. That's why.
Okay. Yesterday it was. Okay. So why is that one working but not the other one?
Change the cable.
Okay. I'm gonna unplug this one.
Supporting issue.
Okay. So we get the minimum extent or the minimum x value, and we can do just the same for the x for the y values. Don't spend too much time on that. The only thing that I want to demonstrate here is while you are also still downloading the data, that we can just get the extent by using the syntax, the maximum y value, and finally the maximum x value. So you can see, okay, our data goes from 83.6 longitude to 88.6 longitude, so east, and then north from minimum from 26.5 to 28.6. So that's about the extent that we are looking at. Now, if we wouldn't have the DEM, just as a thing to do, there is a function called read-open-topo. Okay? I wouldn't do that right now here because it starts then downloading from the server in the US, and that will probably take quite a while if we all do it at the same time. So don't do it. But you can supply the extent, saying, okay, it goes from min x to max x, so just the extent that we just determined, the min y to max y extent. And if you do that, I don't press enter now either, but it would allow you to automatically download the SRTM 90 meter. You can also choose other DEMs if you like. For example, if you type DEM type and you say, let's see here, let's look into the help. Sorry, this is probably very small for those in the back to read, but there are also places in the front. So you can choose from SRTM1, the ALOS World 3D, NASA DEM, the COP30, the COP90 DEM, so a lot of different DEMs to choose from. The only thing that you will need is an API key. That is something that, so you need to be registered at Open Topography. So what this function makes use of is the website and the service of so-called Open Topography. So just check the help in here, and it will tell you how to basically access that data. And it makes it very convenient to programmatically download data. Okay, so let me give you the example that you have, let's say, a lot of glaciers that you're looking at along the Himalayan arc, and you want for each glacier, you want a DEM. Okay, so what you can do, you determine the extent of each glacier, and then you use that function to iteratively download DEMs for each individual glacier. Okay, so that, just to give you an idea what that is good for. As I said, I won't do it here, but just let you know that we can potentially do that, okay? So, what I'm doing is an error occurred, okay? I'm just putting the code here so you can save it. Here, let me just let me just comment it so that you don't run that code right now. Okay, so we already have downloaded the data, and it is here, the DEM. So that's the next thing that we're going to do. DEM equals, and now we are using the grid object command. We learned yesterday that there are different numerical objects, and to store DEMs, to store grids, TopoToolbox makes use of the numerical object grid object. And to construct a grid object, you just need to construct a function, which is also called grid object. So easy. We need to supply the path to where our data is. So it's located in data, and then DEM CRS GCS.tif. Okay. You will see when you do that there's a warning message. Okay. It's good to read warning messages. Some people just skip them. It's also okay sometimes, but in that case, it has a meaning. The grid object cannot derive a map projection structure. This is either because the grid is in a geographic coordinate system, or because now geotiff to mstroke cannot identify the projected coordinate system used. Further, TopoToolbox assumes that horizontal and vertical units of DMs are the same. So it means that what you store as elevation values, it's usually meters. Sometimes you might have feet or something like this. But it's essential that the x and y coordinates also have that same unit. But that's not true if your data comes in a geographic coordinate system. Okay? Then your x and y coordinates are latitude and longitude. So those are in degrees. You will notice that once you plot, for example, the data, you can use just the command image_sc. That just means you plot it as an image, as a scaled image. So it's scaled between the minimum and the maximum value. Okay? So this is the DEM, and when you look at we can also show a color bar. So we see it ranges between something near to 0 to more than 8,000 meters. Yes, that's Nepal. But you see that the coordinates have values 83, 84, and so forth. Okay, so those are not meters, obviously. Okay, so the next step in such a workflow would be, okay, I need to have that in a different coordinate system. And what coordinate system could we use? Does anyone know what kind of coordinate system is, like, you can use it worldwide? WGS84 is a geographic coordinate system. So we need a projected one, could be UTM. Yeah, Universal Transverse Mercator. You have different zones. The good thing is you don't need to care that much about it, which zone and whatsoever. TopoToolbox does that for you. You can just use the function reproject to UTM. Okay, so we use the DEM as input, and the other input that is required is, well, what should the cell size, what should be the resolution of the DEM have? And now it should be, in its original version, when we double click on the DEM, we can see the cell size is something 8.333 times 10 to the minus 4. So that's the very small cell size, but it's in degrees. That's why it's more or less meaningless. So we are providing a new one here, and that's 90 meters. Okay, so I downloaded the 90 meter DEM here just to have a manageable size of the DEM. By default, there will be a linear interpolation done, which is probably the best for elevation values. So don't take nearest or something like this, it will produce some artifacts. What you will also see right now, it's something that I said yesterday, that some functions of TopoToolbox 2 create some warnings. And this is just because we're currently transitioning to a new version. If you don't want to see these warnings, just type warning off. Okay, so I'm just going to put this here. But first we also needed to download the DEM so that in case that was too fast, you can just copy and paste that code to your MATLAB version. Okay, now let's plot the DEM again, like we did before. Image SC DEM. And well, it looks more or less like it did before. It's a bit transformed. Well, that's what we actually wanted to do. I mean, we're transforming that data into a new coordinate system. But what you can now see is that our values here go from 1 to 7 times 10 to the exponent of 5. Okay? And the y values have values something to 10 to the exponent of 6. Okay, so this is in meters, and that's the UTM system. Well, that measure here, let's say that's 3 million basically. That's 3 million meters away from the equator. That's just what it says, okay? And the x value is the distance from some defined meridional line. Okay, so what is not so nice? So what I'm usually a bit into aesthetics also. So what I would really be bothered with, I'm not sure whether it's the same for you, but if you then create a map and you would have these ugly white strips here, simply because, well, when you were transforming your DEM, well, it leaves some blank space around it. If your extent of your DEM is large enough and you can, let's say, cut those away, that's good. So there's an extra function to do that, and it's just called DEM equals largest inscribed grid. So what I'm doing, I'm taking a DEM, I'm calculating the biggest rectangular within my zone of valid values and crop the DEM to that zone. Now these blank areas are gone, okay, and it looks nicer. Just a little trick to pre-process your DEM so that it completely fills the map afterwards. Yes? Those are x and y. Coordinates, don't forget that they are the 10 to the 5 and 10 to exponent of 6. 10 to the power of 6, that means it's just the x and y coordinates in UTM coordinates. Yes? When you turn off the warning, yeah, I usually don't turn off the warning. Yeah, you can just turn it on again then. So warning on. Usually there should be no warnings, and with the new version, they're gonna disappear again. Okay, so we now have the DEM, and we have our drainage basins. So we should have basically 2 variables, except those 4, we actually don't need them anymore. You could just delete them if you like. And now we have these 2 variables, DEM and basins. Now the thing is that the basins shapefile, as I said before, is also in a WGS 84 geographic coordinate system. Okay, it's just the standard problems that you will encounter if you download data. It comes in different coordinate systems. You need to often work in some projected coordinate system. So you will also need to reproject those shapefile data. And this can be done quite easily, and it will be even easier in the newer version. But you can just do that using the command project shape. Okay, so it's an extra function for working with these mapping structures. It requires you to supply the spacings variable, and then you say, okay, it should be projected to the same coordinate system as my DEM. Okay, let's do that. That's it. And well, now let's see whether both are aligned. We plot the DEM. What I'm using this time is I'm using image SCHS. This is a slightly different function from the image SC function. The HS just stands for a hillshade. So you have a colored depiction of your DEM together with a hillshade. Okay, that looks a bit better. Once you have a hillshade, it's easier to interpret just visually. And now let's add also the basins. So you can type hold on. If you type hold on, then your current axis will allow you to add some data. And in that case, we can use the function map show. It's part of the mapping toolbox, and just supply the basins. And in that case, let's just plot the outlines. I will tell you just in a second why. So I'm saying that the face color, so it has nothing to do with your face, but with the facets that make up the interiors of the polygons, is none. Okay, I hope you can see it better. I think I should also plot it perhaps in white. It's actually easier to see, so we can actually add the command edge color. Should be white. It's just like this, that you provide those arguments as argument name, argument value, argument name, argument value. Okay. So, okay, at that point, we have our basin shapefile. We have the DEM, which covers the area of our shapefile. We have adjusted it a little bit. We have reprojected it. And now we have also plotted it. So basically, we already have done our first job, for example, that is just creating a map to see how my data actually looks like. Okay, so I'm removing that. So now let's have a small exercise, and the idea would be that you do that yourself. Two things. I'm going to write those just in the pad. I actually had prepared that in a different way, but so let me go down here. Trip. Exercise 1. Who has deleted all the code? Unfortunately, it's not possible for me to, thanks. What are the minimum and maximum erosion rates in the data? So in the basins data. Remember that this is the field name is EBE underscore millimeters per kilo year. Okay, that's the one first thing. What are minimum and maximum erosion rates that are stored in our data? And the second one, create a histogram of the erosion rates. So remember how we determined the minimum x and y coordinates, and then this is basically showing you how to do that. So let's see how we do it, I would say. So there are different ways to do it. Sometimes you probably also might prefer, to make your code easy to read. In that case, I would just suggest to create a new variable that contains all your erosion rates, rather than working on the basins variable all the time. So you could say, okay, we create a new vector, ER, for erosion rates, and we create this using basins, and then it was EBE, right, something like this, and it was this one here. Okay. So this creates a row vector, ER, with 186 entries, so as many as there are basins. And we then can use that one to determine the minimum erosion rate and the maximum erosion rate, and to calculate a histogram. And the histogram function is also called histogram. It takes a vector and then creates a figure that is now plotted into the existing axis. We don't want this. So now you can see that's the distribution of erosion rates, ranging from near to 0 to up to 10,000. So a few samples have apparently very high denudation rates. So 10,000 millimeters per 1,000 years means 10 meters in 1,000 years. That's a lot, really a lot. But in order to make that a bit nicer, just as something that we should always do, label your axis. There's a function xLabel. So we could call this, let's call it denudation rate in millimeters per kilo years. Okay, and what's on the y-axis? What shall I write for the y-axis? Let's just call it counts. That's what it is, actually. Okay. Okay, did that work for most of you? Sounds good. Excellent. So let's go on. So in general, TopoToolbox offers you a lot of possibilities, basically also to create, let's say, publication-ready figures. Like the histogram that I've just shown is something that you just could have as a figure. But in fact, you can also create a lot of maps and stuff like this using the visualization functions. What I will just briefly show, because it's often required and it's also fun to do that, is to show how you can also create actually a map with your data now in MATLAB. So I would usually start with plotting the DEM, okay? But there are a lot of other options. So when I use image SCHS, the default view that you will have is that one. So it takes the color map, for example, which is the Parula color map. It's the default MATLAB color map. Perhaps it's not that nice. It actually is not so suitable for terrain data, okay? So instead, you could use a different color map. And this could be the following. So what you need to do here, it will be different in a new version, but is leave or put an empty array in here as a second argument. The second argument lets you control what the coloring of your map will look like. So whether it will be colored to gradient. So by the default is basically like this. You have a hill shade based on a DEM, and the coloring is also based on a DEM. You could also say, okay, the coloring should be follow the slope, for example, of the DEM. Okay, but let's have a different color map. And so you can use, for example, land color. Okay, so this looks a bit better. And also you can say those ticks or those x tick and y tick values here, that's not so nice with a 10 to the power of 6 somewhere up here. You can do that also differently by using just a simple command which is called nice ticks. Okay, so now your it's labeled a bit differently. And well, in fact, you could also add, we're not going too much into detail here, but you could also add a scale bar. Okay, and now let's also plot the outlines of our basins. We have done that before, so I just use the map show command that I did before. And here you have your first map. Okay, I'm gonna copy and paste that into our pad, so you can also use these commands. Okay, so that was so far pretty easy. We could have done that in any GIS actually as well. Now let's start doing some computations on our DEM. And what we want to do is calculate flow directions and flow accumulation, stream network delineation, and stuff like this. Okay? But before we do that, there's one thing that we need to adjust, because I noted that there's one issue in the data, and let's take a look at it. The problem is one thing, basins, in the basins, data, basins, and then area. So there's one, so basins has one attribute, and that's the catchment area, actually, in here. And one of those has a very, very small catchment area. So the catchment area is in square kilometers, and usually your catchment area should be bigger than 1 square kilometer, even larger than that. So that means you would have a very small catchment area where, in particular, if you're in mountain areas, you have a single landslide, and that would just destroy your entire value. And I think in terms of its erosion rates, it's also unusual. So we are safe to delete that one from our data. In that case, so the minimum, min R, let's call it like this. And then just something that you learn on the fly is linear indexing. So the second output of the minimum command gives you also the position of where the minimum is found. Okay? So when we just run that, it says, okay, the minimum area is 0.44, and it's located, it's the 19th entry, okay, of our basins shapefile. So the 19th is this one, and let's see where we have our area stored. Yeah, I guess you can believe me that it's somewhere, but yeah. I don't find the area. Here it is. So you see, all the other basins have much larger sizes, except that one. That is really small. So let's kick it out. And we can do this by just saying, okay, basins, EX, okay, is empty, like this. So once we do that, we have only 185 basins left. Okay. Remove one of the basins. Okay, so now we're ready to continue. So in order to calculate flow directions and flow accumulation, as we heard yesterday, we need the flow object, and we can simply calculate one using the flow object command, like this, and using the DEM as input. Okay? That's basically all. There are some more options that we could talk about, but for now, I think that's all we need. What is different to when you do that in a GIS is that in QGIS or ArcGIS, you should use or you must use some filling before. Okay, so you fill the DEM so that there are no topographic depressions, no sinks where your flow would get stuck and not be able to escape. The fill things option or fill things algorithm basically raises those pixels to a higher location, so to make sure that from every pixel there is a downward path to somehow to the edges of the DEM. That is something that is done automatically in the flow object function. So if you open the function itself, which you could just do by open flow object, then you can look at the code. Then you will see that exactly that happens within the code, but a bit of a different way, which I won't talk about today, but it just gives you a better routing through internal things than just by filling them. Okay, so FD, let's take a look at our workspace is now a new numeric object. It's called flow object, and we can take a look at it just by double clicking. And you can see, well, it has a certain size. So that's basically the grid size from which it was derived, so the DEM from which it was derived. It says it's a single direction object, so it could also be a multiple direction object. And then there are a lot of numbers, so EX and EXC. So usually you don't have to care about what is actually in here. Just what I want to note here is there is no grid stored in that object. It's just the links between individual pixels that are stored. And these links are even sorted in a way that makes any computation on those links, either in upstream direction or downstream direction, super fast. So that's the rest is basically the same as in a grid object. But that's what actually is stored in a flow object. And based on that, for example, in order to calculate flow accumulation, you can use the command flowacc for flow accumulation, and it's computed like this. And then we can directly plot it, image SCHS. Let's use this one now, and now let's plot the flow accumulation we used as a second argument into the image SCHS function. And color map is, let's take flow color. Okay, so that is a color map that ranges from white to blue. Now there is a lot of white in here, apparently. Why is that? Obviously not everything is white, but why is that the case? Pardon? I didn't get... no, not necessarily. Of course, there's a lot of flat regions here in the Ganges or in the foreland. But flow accumulation has a very weird distribution, okay? So you have a lot of many small values and then just a few very large values, okay? It's those pixels where a lot of water comes together. So some of those major rivers leaving the Himalayas, that's where you have very high values. So most of the data range, or the majority of the pixels has very low values. And so they are all plotted more or less white. So once you zoom in, you can see, okay, there are just these individual paths that have relatively high values. You can diminish a bit the effect of that by, okay, plotting, for example, the square root. So you take just from each flow accumulation value the square root, and that decreases a bit the effect, but just a bit. So you still see it ranges from, let's say, 1 to something 2,500. Now you can see even more of those. And if you want to compress, let's say, the distribution even more, well, you could just also use the logarithm instead of the square root. And now you can see a bit more. Now it just ranges between 0 and 15 or so. And if you zoom in, it just doesn't work on my side, apparently. Okay. Now you can see the individual flow network, okay, which looks like this. So each pixel in this image, I mean, it's shaded because that is derived from the DM. The coloring is based on the logarithm of the flow accumulation. And well, what does flow accumulation say? Basically, it gives you for each pixel the upstream area. Okay, so the catchment area for each pixel, which is usually a very good proxy for the discharge. Okay. Now, based on the flow object, you can now extract the stream object. I talked about this yesterday, that the stream object is actually a subgraph or a subnetwork of the flow object. The flow object contains like every connection of every pixel to every other pixel or to its neighboring pixels. Now the stream object does that exactly the same, just for some selected pixels. For those for which that you consider to be stream pixels. Okay, so we can do that using the stream object command. The stream object derives from the flow object. And you could just say, okay, I want a stream or streams to begin where the upstream area attains a certain value. Okay, so where, for example, 1,000 pixels flow together, that's where a stream actually starts. Or we could create a larger offset here. Let's say 10,000, or let's say even 100,000. And if you do that, you get the stream network. Okay? So if we would have chosen a different value, so let's say not 100,000, but 10,000, then you would get a much more detailed picture of the stream network. And if you choose an even smaller one, 1,000 pixels or 100, then of course your stream network becomes very dense. Then your computer will become also a bit slower because plotting all those paths and links then will be difficult. Okay, so we learned now how to derive a flow object and a stream object. One of the, I think, strength of TopoToolbox is that you now can do a lot of things with these stream networks. And I want you to explore that a bit by yourself. So for example, let's go back to our pad, exercise 2. So first of all, use the function plot stream order. Then check the function modify. So it's called modify, and learn how to plot or to create a stream network, or to learn how to modify your stream network so that it only contains rivers with a stream order of 2. Okay? Then also use the command plot dz. Check the help to see what other input arguments you need. Okay. Okay, so that's a small exercise. And I think we do that one, and then we have a short break, I guess. What? Yeah. Yes. Oops. Yeah. Yeah, you could do that. Could just be automatic saying this threshold and everything should be thrown. Yeah. Yeah, you would need to code that by yourself, basically. Yeah. No, no. Those are the too simple to have their own function. That's only required for, so for stream order, let's take a look at it. So there is this function plot stream order, okay? It should just work with one argument, I think, I hope, yes, okay. So it calculates the stream network, or not, well, that's already there, but it calculates the Strahler stream order. Okay, everybody knows what Strahler stream order is? Yes, of course, yes. So streams with no contributing stream get the value 1. If two first order streams flow together, the next one gets order 2. If a stream with order 2 has a confluence with another stream order 1 stream, then 3, 2. It remains 2 exactly. And then if you have 2 that to come together to have 2, then it becomes 3. Okay? So usually the orders do not become very high. There are other ordering schemes like the one of Schreve or so, which get much higher value. So here in that case, of course, that depends on the threshold for the minimum area, but here it just attains values of 5. So I think the Rhine has officially some either 6 or 8 also as a stream order. So, but there are some extra options here in order to see, well, what kind of options do you have, just check the help of individual functions. So when I type help plot stream order, then usually for each function there is a text that describes how that works and explains, well, what are the input arguments and what are the output arguments. And then mostly there's also some short text describing it. So for example, here you also have the possibility to input so-called parameter name value pairs. And now let's see, for example, there is an option legend. Let's see if it works. Plot stream order. And we could just say, oops, legend equals false. Then there is no legend. Or you can say it should be true. Then there is, of course, a legend. Alternatively, you can provide a color map. Now, that's a bit more difficult. Let's see if that works. So it just says here, if only one color should be used for all streams, but only the width should be changing, you can use just one RGB value. Okay, let's try that. Color map, 0, 0, 0. So often you provide colors as just an RGB triple. red, green, blue. Everything is 0, so it ranges between 0 and 1. If everything is 0, then that means it's black. Okay, so you get a map that looks like this. And if you like, you can also create a stream, an image, SCHS map. And then you have a map like this, okay? It's sometimes better to plot it like as a, if you adjust the width of your river network, it's easier to read, okay? And perhaps it's nicer also to have them in blue. In that case, remember that it's red, green, and blue. So if it should be blue, then there should be a 1. And now you have a blue network. Okay. The other thing was to modify your stream network in a way that you only get second order streams. For that, check the help of the function modify. Okay, help modify. And what you get is a pretty long description of what this function does. In my experience, a lot of students tend to not read the help, but sometimes it's helpful to read the help. And here, well, for modify, it's really a bit long, but it might be worth just going through the list of possible parameter name values to see what can be done. For example, if you just want to extract parts of your river network that have a stream order, a certain stream order, well, you can do that. You can select parts of your network that have a certain distance from the outlet. You can, for example, say, okay, I want only the stream network that is, for example, upstream to some mapped faults also. So as a tectonic geomorphologist, you might be interested in, well, the stream network that is upstream of a normal fault, because it might be different to that which is downstream. There are even things like just to extract all tributaries, the left tributaries, the right tributaries, and so forth. So a lot of stuff. So for example, let's call this S2 equals modify S, and we just get those stream orders that have, or those streams that have a stream order of 2. Plot S2. Okay, so those are all the second order streams. You can do the same for the first order streams, for example. Hold on, plot S1. And then you have both. Now they have a bit of a different color now. Okay. You can also say, okay, I just want just the trunk streams, ST, let's call it like this. That one has its own function. It's just called, because I need it that often, it just has its own function, S. So that will extract for every drainage basin just the trunk river. And the trunk river is the river that is just the longest river. Okay, plot ST. Okay, now you have a couple of trunk rivers for each basin. So you see you have a lot of basins, especially along the fringes of the DM. That's just normal. Now, you might be interested just in the longest trunk rivers. Let's say 1, 2, 3, 4. Then you can take the function st, and that one has a weird name, k largest concoms. That was very much at the beginning when I wrote TopoToolbox, so that, I don't know. Well, it makes sense because in a graph theory terminology, it makes sense to talk about drainage basins as connected components. And if you have the largest components and you want to have the k largest components. So in that case, I want to have like the 4 longest or largest trunk streams. Okay, so when I do that, now I have just the 4 longest streams. And let's go a step further. Next step could be then, okay, now I want the drainage basin for each of those. And then, okay, let's create a new grid. Let's call it, so there's a function drainage basins. Now this requires, again, our flow network, FD, the flow object. But as a second input argument, it is possible to use a stream object, okay? So in that case, you directly get the drainage basins. And I think that's one of the major strengths, that you define drainage basins by their rivers. I mean, a drainage basin is defined by the river. So you could also say, okay, I want the drainage basins just for my second order catchments. Remember that we got this stream object S2. Where did we do it? Like here with the modify command here, S2 equals modify stream order 2. Now when we calculate the drainage basins based on FD and S2, well then we get all those sub-basins. Now they have a weird coloring because MATLAB starts coloring from the left upper corner and then goes to the right. We could just shuffle those labels, shuffle label. And then we see how that looks like, okay? So these are all the drainage basins for my second order streams. And it's very easy just to do the same for my first order streams. So you see, it's just a few clicks to get these data. Now working with the erosion rates and our DM jointly. Okay, so I will now go a bit through some of the stuff that where I also struggled a little bit with when preparing that course, okay? And so you will see that it's sometimes not so super easy, but I'll explain what's happening. Okay, so let's plot the DM once more. And hold on. Then we plot the basins. Map show, we have done that quite often now. It's like this. Okay, so that means in our basin shapefile, it's a polygon shapefile, but what we actually need is the outlet locations. Okay, so where have where the samples actually taken? Okay, of course we can see that here. Okay, that must have been somewhere down here, or whatever drainage basin outlet it is. That's the lowest point, obviously. But where is that information actually? So that information can be found in the basins file itself. And there is a, let's see, where is it? Some some X and Y data. We used it before when calculating the extent. It's here. So there's 2 columns, X WGS84, Y WGS84. So when we reprojected the shapefile, well, then we just reprojected that first, or the second and third column here, X and Y, which contain geometry. But obviously, in the attribute list, there is this additional information on the point locations where the actual samples were taken. So in the next step, we also need to convert those data from geographic coordinates into these UTM coordinates. And let me see how I did that. So sometimes code can become a bit tricky to read, but as long as I just talk at the same time, I guess it's understandable. So we take the function proj forward. This is a function that comes with the mapping toolbox and uses the internal projection functions. We need to use the georeferencing that is in the DEM. That's a bit tricky here too. So it's a DEM, there's some georeferencing mstruct. And now we use both the basins, Y, WGS 84, and basins X, WGS 84. Okay. Now what does it do? So it requires, proj forward requires that you have some projection that is stored here in the DEM, and then it requires latitude and longitude in that order. So not longitude, latitude. So that's why it's Y and then X. Okay, latitude, longitude. To then convert those coordinates, those point coordinates, into two vectors, which is X and Y. Okay, so we now have two vectors, X and Y, so the same amount as we have basins. Okay, so let's plot those together with our DEM, and at best we use our flow accumulation grid. Let's use this one here. So, and we plot our locations, X and Y, with some crosses which are colored black. Okay, so you can see them here in this map. And when we zoom in, you can see that, I hope you can see them, they remain small. Let's get them some different color also, like this, or not color, but a different symbol, so you can see them better. So it's here's one, there is a sample, here, and so forth. So what can be recognized from here when we plot those two things together? Let's go somewhere else, somehow like here. Apparently the sample location was here. There's another one. So what can be recognized? What can be seen? So either the samples were not taken along the river, or the rivers are wrong. Okay, because actually what you do in that method, you go to a river, somewhere along the river, you take a sample with sand, and from that sand sample, you calculate the 10 beryllium concentrations and so forth. But obviously there is a mismatch between those reported sample locations and our flow networks and what we have computed as where we would have the rivers. So there are these two sources, possible sources of error. Either GPS locations didn't fit, or our DEM is rubbish. Could both be, or both, actually. Now what you would do is you need to somehow snap those locations to the river network. Okay, and that's something also that you can do in any GIS. There's a snap to stream function both in ArcGIS and in QGIS. So let's try that. There's just TopoToolbox offers exactly the same. Let's do that. So we want some new locations, xn and yn. And the function also gives me, and I just tell you what that is in a second, x. And then we call the function snap to stream. We need our stream network. And, there's one thing that I forgot to do. We need to recalculate the stream network. S equals stream object FD. And then there's one thing that I want to do. I want to have the minimum area so that it's definitely smaller than the smallest area that is in my basin shapefile. So we should have a network that is as fine-grained as the drainage basins that are actually located in my basin shapefile. So we calculate the minimum basins area. So the minimum, we saw that before, is something about a square kilometer, and those values are also reported in square kilometers. Okay, so what we need is in map units, actually. So we need to multiply those by 1,000,000 so that we get from square kilometers to square meters. And what else do we need to do? I think perhaps we can even we multiply that by 0.8 just to be on the safe side, that even a bit smaller catchments are located, or that we delineate even smaller catchments. Now let me think. Yes, and there's just that units, I have to tell stream object, because by default I say, okay, everything that where 1,000 pixels flow together, that's where stream starts. So I think in terms of pixels. But in that case, I'm providing a map unit, so in terms of square meters. So I have to tell stream object that what I'm supplying here has map units. Let's see if this works. Okay. Now back to snap to stream. We take that stream network and snap the locations X and Y, so the outlets of these streams, to the actual river network. Let's do that. It takes a bit, but not too long. So what I get is two new vectors, xn and xyn, which contain these new locations. So plot S. This takes a bit longer now, because actually it's very fine-grained. So it's quite a huge and dense stream network. And then we would also plot the old locations, x, y, and the new locations. And you see that there are some locations that are pretty close to the stream network. So snapping actually doesn't require a big distance to snap. In other locations, it's a bit different. So here, for example, or here. No. But one thing, what we should do is to test, well, did it work well? Does it actually, so what about this location here? It snapped to this stream here, but is that actually true? It could have also snapped to the other one, to the bigger stream. So what could be an approach to test whether it snapped correctly or not? Does anyone have an idea? How would you test that? I mean, it would be, you would have exactly the same problem if you would work with hydrological gauge data, for example, which would not align with your stream network, and you would want to just attach your gauge data to those locations. Well, gladly we have some additional data, and that's the area. Okay, so in that basins file, there was that extra attribute, which is called area. So we could actually compare the upstream areas at those snapped locations with those that have been reported. Okay? Let's try that. First of all, and that's why we need this EX. So EX is a linear index into my DEM. So you can index into a DEM in several ways. In that case, we have coordinates, so we know where this is. But we can also say, okay, given just when we count just the pixels, starting from the left upper edge, 1, 2, 3, 4, 5, and so on, and then the next column and so forth, then I just have one number that describes a location. And that is exactly what EX does. It's just one number, or in that case, 185 numbers, so for each basin, and gives you a linear index to sample the DEM. Okay, so we can use that to determine the flow accumulation. So let's do that. A equals A dot set EX. So what does that mean? Well, I took A, which is this grid object A, which contains the flow accumulation. We computed that before. I have to index into, or just use the matrix which stores these flow accumulation values. That's why I use A.set. And then EX to index into the grid. Now, the flow accumulation grid just stores the number of pixels that flow together. Okay, so what I need to do is to compute the area. So it's just DEM cell size squared. So we have the DEM here, we extract the cell size, and we square to get the size, the area of each pixel. Okay, so we have A here as a new variable, which contains the area, the upstream area, for each of these snapped locations in square meters. Now let's take those that have been reported. They are those that we find in the basins file, basins area. And they are reported in square kilometers, so we have to multiply them by 1 million. So, and at best, both should actually be the same. Okay, so we can just plot one against the other, for example, using the command scatter, A versus AR. Okay, and let's use a reference line with a slope of 1 and an intercept of 0, and we see so let me just adjust this a little bit. Axis equal. That it works for some, okay? And then a couple of pixels are completely off. Okay, so apparently those are the ones that we calculated on the x-axis. That's the area on the x-axis, and that is the one that has been reported. It's okay for some, but for some it's completely odd. It just doesn't seem to fit. So that's a problem of the snapping algorithm. It just uses or searches for the nearest stream pixel and snaps to that stream pixel, irrespective of what that stream pixel actually tells us. Okay, since I face this issue quite often, I thought, okay, let's write a function that overcomes this problem. Or not even an own function, but let's use and add an extra option to the snap to stream function. So let's run this again. And so snap to stream. We have x and y that we snap. And now we can add some additional options. Okay, so what we need is for every pixel of our stream network, what was that again? It's area, a node attribute list of areas, get null as A. So what's happening here? What I'm extracting is for every node in my stream network, the upslope area. Again, I need to multiply those by dm cell size to the square to be sure that it's in square meters. Let me just see. I have to check whether it's, if I do that correctly. Oh, well, I have it also here. No, it's the other way around. So it's not area null, but null area. So it's a node attribute list with all the areas. And then I also input the areas that have been reported. So null point area in that case. And those are these areas reported, those ones here. Okay, so it takes basically all the upstream areas along my stream network in this first part, and then it also takes the upstream areas reported for X and Y. Now when we run this command, it means that snap to stream searches in the near neighborhood of each X and Y pair for a pixel that has the upstream area, or where the upstream area fits. Okay, and it tries to optimize that somehow. Let's see whether it works. Let's extract upstream area again, like this, like we did before, and then use scatter to see whether it fits. And now you see that it fits. Like every sample location has been moved to the most, let's say, or to the best location nearby, optimizing or minimizing like the distance that it has to snap and the difference between the reported areas. Okay, so now we can be sure that all these locations are correct, and comparing these two suggests that we are actually quite fine. Okay, now we are actually at a point where we can use this data to compare basically what's upstream of my sample locations and what is reported as erosion rates. Okay, but before I do that, let me copy all that so that you can also use it in your code. So one. Okay, so we were re-projecting our outlet data, but then plotting it, realized, okay, it doesn't match. And then in the end, we modified the snap to stream function in a way that it forces these values to match. Okay, so one thing that we can actually now do, let's calculate the drainage basins as we have learned it before, using FD and EX. Now it also, the drainage basins function not only takes S as a second argument, not only a stream object, but also just this linear index. And in that case, it gives us a nice matrix which shows the locations of all these drainage basins. Okay, so what we want to do in a last step now, or not in the last, but in the second last step, is to compute some candidate variables that we can actually use as predictor variables to predict erosion. So what kind of variables would you test? What do you think? What correlates with erosion? Well, these average denudation rates, if you were asked to model that. Discharge, okay. But why discharge? Pardon? Exactly, it needs to carry this, the sediment, but our erosion data, it's actually normalized, right? It's just millimeters per kilo year for every, so it should not directly scale with the upstream area. Precipitation might be something that we could use. So the more precipitation, the more erosion, exactly. What else? But that relation usually doesn't hold so well, I have to say. That precipitation is very, and I mean, you have a lot of more force basically to erode, but on the other hand, the more vegetation there is, the more precipitation you have, the more vegetation, the better protected is the ground. So the deforestation might work, but consider that we are working on timescale here of hundreds to thousands of years. So then deforestation might not matter that much. So one of the easiest metrics could be slope, for example, right? Just using the steeper a catchment, the faster it erodes. That could be an option. I would say let's just test that, okay? So to do that, let's calculate slope. G is, there are different ways to calculate slope, so we can use arc slope, for example, as a function. It takes the dm and returns another grid object, G, which contains the slope. Okay, let's plot it. G, like this. No, let's just use the default color map. Okay, strange, what's happening here? Look at those values going from 0 to 16. Okay, that's a pretty steep slope that seems to occur somewhere locally. Let's just have this range between C-axis. Between 0 and 2, perhaps. I mean, it's the tangents that is stored here, so that should be a more acceptable range. And then you can see when you plot that, that seems to give you a quite good distribution of slope in the Nepal Himalaya.
Slope is like angle of repose, sir?
No, in that case, it's just a topographic slope. The angle of repose would be something for these systems like 30 or 40 degrees. One could compare that, the actual slope compared to the angle of repose. One could do that. A lot of areas would basically be much higher than, or steeper than the angle of repose. But that could be a possibility to check the percentage of the area that is steeper than the angle of repose. But here I would just say let's calculate for each drainage basin mean gradient. Okay? And there's a function that you might know in GIS also that does that for you. It's basically zonal statistics. Okay, if you have a drainage basin, you have some polygon, some outline, and then you just calculate some underlying or statistics of the underlying raster using some aggregation function. That could be the mean, that could be the maximum, the minimum, the median, whatsoever. We can do that also, but it's the thing is that if you do that in ArcGIS using zonal statistics, you will get wrong answers. Because what we have here is nested data. Some of these drainage basins are located within other drainage basins. And that causes a problem with zonal statistics. So I wrote an extra function which does that. Let's call it stats. And it's called drainage basin stats. Okay. It also takes FD, our flow direction object. It takes EX. Now those are the outlet locations of each drainage basin. And then I need to take a look at it myself. We can add some grids. Okay, let's do that. So for example, let's take slope. And our slope grid is G, the one that we just calculated. Now let's do that. This requires a bit of time, not too much, but okay. So what is stats now? Stats is also a structure array, like the basins file. But this time, it contains our drainage basins, the ones that we delineated. And it also contains a lot of other data. So for example, upslope area, the centroid, and then there are a couple of fields that all start with slope. Okay, there's slope mean, slope standard deviation, slope the first percentile, fifth percentile, 33rd, median, and so forth. So a lot of statistics on our variable slope for each drainage basin. And I think, or a possible hypothesis, I said, would be, well, I guess that those drainage basins erode faster that have steep slopes. Okay, so whose average slope is high, one could say more precisely. So let's test that. So we have our basins shapefile. Let's extract or use well, we have that before, the erosion rate, right? That's here. Let's calculate that again. Okay, we have our erosion rate and the mean slope, let's call that average slope, is stats slope, and then we take the, well, not the mean, the median, but the mean. Okay. And actually it should be possible that both correlate. So we would argue that AS, well, let's use scatter, correlates with the erosion rate. Do you think that works? Let's see. Okay, it doesn't look so great. Or, I mean, we have slopes that range from 0.25 to up to 0.75, so we have some really low-lying, relatively low gradient catchments. And then we have some catchments that have, I mean, one would be an average slope of 100% of 45 degrees. That's quite steep. And we have a huge range of erosion rates ranging from more or less 0 to up to 10,000. Okay, we can tweak it a little bit by plotting it in a log or in a log axis, at least that we, well, let's just do it like this, that we look at the logarithm of the erosion rate. Then it seems a bit more like we get a correlation, okay? There is a function, ls line, I think, just to produce a least squares fit. Okay, it's not so nice. Okay, it would definitely be significant, probably, in terms of the steepness, but no one would actually say, okay, that's a great relation that we see here. So perhaps there's something wrong with our predictor matrix or predictor, the mean slope. Perhaps we can also look at the median. Perhaps it performs better. Not really. Perhaps it's just the percentiles, like the upper percentiles that matter, like the 95th percentile of the slopes. I'm just guessing here. Oh, it's even better. That's a bit surprising. I haven't looked at those data before, so it's. But what I just do is fishing for correlations. Okay, it's like it's done by some people, and what you do is basically you go through all potential predictor variables and try to find the one that best correlates. But that's not a good approach. Why is it not a good approach? It's like what is also called p-hacking. But what you do, usually you should start with a hypothesis first, and you test it, and that's it. Of course, that's not how real world looks like. But what you do here, you're testing multiple hypotheses, again and again and again. And if you do that 100 times, and you're testing, let's say, at a significance level of 95% or an error probability of 5%, that means in 5 cases you will probably find a significant correlation, but that's actually not true. You search for it like 100 times, and then it's quite likely that you find a significant correlation. So that would not be actually the way to go. Nevertheless, it can happen that you say, okay, in an exploratory study, I have been looking through all my predictor variables, I found that one, and now I'm trying to find an explanation for that. But now find a good explanation why the 95th percentile of the slope distribution in my catchment determines the erosion rates, the long-term erosion rates. I don't have a very good explanation for that. Perhaps erosion mainly takes place in those locations that are particularly steep or so. I don't know. Okay, it could also be good just to start with a good hypothesis. To go through developing such a hypothesis, I think I wanted to do that, but it will take too long, I guess, to do in the time that we have. So I will just very briefly go through a few slides that show you what I mean. The fun thing is that there's also a little guess game here. So what I try to do, and that's something that I would also encourage you to do usually, is to find a good theoretical model for your regression model, for your statistical model, and test that. And luckily, in geomorphology, we have such a model. And it's based on the so-called stream power model, which is actually the basis for most landscape evolution models. So this is just a result of such a stream power model simulation, which generates a kind of landscape. And I just want to very quickly go through that, not bothering you too much because it's getting too late already, but just to give you an idea how that works. Now, when we think of landscape evolution and what determines erosion rates, right, then we need to think of the processes that actually occur in a landscape. And there are actually 2 main processes, or let's say 3. But the first one is everything that happens on hill slopes. Okay? Usually hill slopes get some rounded form. And usually these are kind of diffusional mechanisms, landsliding and stuff like this. Then you have the rivers that in size. Okay? And then finally, you have uplift. Okay, so the mountains go up, hill slopes erode, and the rivers in size. Actually quite simple. This can be cast into some equations. I won't go into much detail here. They look more complicated than they are. It's actually, we have some elevation change at every point in our DEM, let's say, in our landscape, which is a function of uplift. That's what I just said. There's new lithology coming up. The whole stuff diffuses due to hill slope processes and because of rivers that incise into those rocks. And, well, these 3 mechanisms, basically, when you do simulations with that equation, you can get quite some intriguing topographic or some simulated DEMs, if you like. I just skipped through that and come to the point where, well, when we take that idea of landscape evolution, so every pixel or every location changes its elevation due to uplift, to hill slope denudation, and due to river incision. And when we assume, okay, let's don't care about hill slope diffusion. and all that. Everything is driven by the rivers that in size. And then that's quite a good assumption for some mountain landscapes where rivers provide the pace at which a landscape erodes. Then we can just remove that term, have just that term here. And this is actually the stream power model. Okay, it just says that at any point, the elevation change is due to uplift, or let's say at any point along the river, due to uplift minus the incision. Okay, this is actually one of the most important laws in, or I wouldn't call it law, but it's rather, people call it the stream power incision law, but it's rather model. Law is a bit exaggerated when you compare it to Newton's law also. But it just states, okay, the incision is a function of upstream area and slope. We can take that, we skip that, but we can take that and go a step further and say, okay, in a landscape that is in equilibrium with itself, this means that both uplift and incision basically balance themselves out. Okay, so you have still uplift, and we have that in the Himalayas. They uplift with a rate of 1-2 millimeters per year, and at the same time the river's in size. If they are both in balance, that means that the elevation along these rivers doesn't change, even though things change because you have still uplift and incision. If you have such a condition, you would classify it as a steady state. Okay, a steady state between uplift and incision. And that makes, if we use that assumption, it's actually pretty easy. Then we say, okay, dz over dt, the rate of elevation change is 0, and that allows us to solve this equation here, u minus k times and so forth. The stream power term is 0. We can rearrange all that and solve for slope. So this gives us, or tells us basically, that slope along the river is a function of upstream area. Okay, so we get an idea of the steepness of rivers from that. And this is encapsulated in that value ks here, that if you assume some parameters here, I won't go into detail here, I'm sorry, but that ksn basically describes the actual slope divided by what you would expect it to be. Okay? So the slope that you measure versus the slope that you would expect. And that's what is called the steepness. Okay, so what we derived is there's a landscape evolution model. From that landscape evolution model, we just look at the fluvial domain. And in the fluvial domain, we say, okay, we assume steady state. And if we assume, and under that assumption, we can basically solve for the expected slope. And then we can compare our actual slope versus that expected slope. So that is something that you can do with TopoToolbox pretty easily. Let's try that. There's actually also just a KSN function. KSN. And what does it require? Well, there's some suggestions here. It requires S, our stream network, and DM, and A. So DM for calculating the slopes, and A for calculating the drainage area. That gives you K, and you can see that this is a pretty long vector right now with more than 1 million entries. It gives you for every point along the rivers an estimate of the river steepness. Okay? And now we use that as a possible predictor for estimating or for modeling our erosion rates, because it makes sense to say, okay, under these assumptions of river incision and so forth, we assume that rivers are more rapidly incising where they are steep, and that should correlate better with the erosion rates that we have observed. What we need to do is to convert our what is called a node attribute list here, so all these KSN values, to a grid object. there is a function which is called stream object to grid object. We take S and our node attribute K, list K that we just calculated. Okay, now we have again a grid object that contains all these KSN values, and these are the ones that we now use when we calculate our statistics. Okay, so we again calculate our drainage basin stats based on our flow directions, EX, and this time we not only look at slope, for example, but we could also add KSN, which is retrieved from K. Okay, let's do this again. So it's a bit slow because it needs to go through all drainage basins, through all 185 basins, since they are nested. That's the issue here. So it has to process them in a loop, otherwise it would work differently. Okay, so now stats, that's exactly the same as the one that we had before. Where is it? It's here. Except that we now have some additional columns where again we have KSN mean, KSN standard deviation, KSN all the percentiles, even stuff like the kurtoses or the schooners. So all kinds of metrics that describe the distribution of KSN in our drainage basins. Now we can again, let's average KSN, okay, AK. And instead of using slope, we now use KSN, like we define it here. Okay, is it this? Just doesn't look much better. Did I do something wrong? Let's see. Well, not really. It's not getting so much better, okay? But if you look at studies that have done such an analysis, that's exactly what they do, okay? Using mostly KSN as a metric, of course, what we could do in addition is, for example, to look at what is the part that has been glaciated or so, or looking at, I don't know, the percentage of glaciated catchments. But that makes things even more than complicated. Here we would have just a relatively simple model, just with one predictor variable, KSN. So you see these are values that range between 0 and 450. That's about the range that you would also see in the literature. And then on the y-axis, you have the logarithm, in that case, on the denudation rates. It doesn't look much better than actually looking at gradient. Because why? Because both are, of course, highly correlated. KSN is very much correlated with gradient. However, it has this theoretical background, which makes it a stronger argument, let's say. So at last, well, we might, again, want to fit a line that still doesn't look too great, okay? But the question is that actually a good model? Yeah, I mean, it looks like we could fit a straight line here. Now we are leaving a bit the part where we do terrain analysis, but go a little bit into statistical modeling. What's the problem with that data? With these data points that you see here? Actually, there are two problems. Yeah, it's a question whether it's linear. Actually, it's difficult to actually judge whether there's a linear relationship. It's not, right? We have a log transformed y-axis. That's already a big problem. People like to do that they simply log transform the y-axis, but actually it's not allowed to do that with a least squares regression. That's what the function ls line just did. So for drawing and fitting that line, it uses a least squares regression. The other problem is that, I mean, looking at the data let's do that again. Without taking the logarithm, I mean, it even looks worse. Okay, it looks like that. First of all, we have a big outlier here. It's something that, in that case, I guess one could remove. There is another big outlier, okay, that exists. And definitely in the original units, it's not linear. But that's something that is expected in that areas, okay? That at some point where your rivers get very steep, they won't get actually steeper. It's just they erode faster, but they won't steepen anymore. So in the end, you could expect that there is some kind of relation that shows an increase in erosion rate, and then it goes up. Then it becomes independent of the steepness. But also it seems like there are a lot of catchments that are actually quite steep but are not eroding that fast. So perhaps it's good to look at the logarithm like this and fit a straight line here. But the thing is, okay, you are not allowed to do that because it's in a log space. So what could one do? That's the problem with statistics. There's always assumptions behind, and in the end, you are not allowed to do anything. You might remove some outliers, and I think it's fair to do that sometimes if you have a good argument for that. An option could also be to use robust statistics. So there is an extra branch in statistics that says, okay, if there are a couple of outliers, that's okay, we can deal with that. And then iteratively optimizing the model by reducing the impact of the outliers. Another option is to use not least squares, okay? Instead, you could use a quantile regression. Anyone heard of a quantile regression? So it means you are modeling not the average, not the mean, contingent on the predictor variables, but you calculate the median contingent or on the values of the x-axis as a function of x, basically. It has the advantage that there are no assumptions about the distribution. So it doesn't need to be normal distributed. It doesn't have any assumptions about, and that was one of the things that the other data also, when you looked at it in the original space, but it's even evident here, it's that it goes like this, like a trumpet, okay? Relatively low variability on the left side, and then the variability increases when you go to the right. You have that kind of behavior of data quite often. It's called heteroskedasticity, meaning that the variability is itself a function of x. Also something that we should not have when we use least squares. Okay, so the option is, let's use quantile regression. That's much easier. And I have in the zip file that I distributed, there is a function. It's called quantreg, okay? And it's doing exactly that, quantile regression. So that's the last step that we do. Let's model that curve here using quantile regression. So let's take a look at this function, quantreg. So it has not been written by me, but by Aslak Grinstedt. He is a glaciologist, actually, working a lot in Greenland and so on. And he has written a lot of good code. So here it says, let's use quantile regression, and this is the code. Okay, let's just use the first part, no, until here. So what is x? Well, that's basically KSN. Where is it? What was the name of that variable? I don't remember. AK. And y is our logarithm of the erosion rates. And actually, quantile regression can not only just model the median contingent on the predictor variable, but just also any other quantile. So let's say the 0.1 quantile. But okay, let's use the median, which is 0.5. Both must be column vectors. So some of them are still a row vector. So the double point, that's basically forcing the vector to be column vector. And now what this function returns is a variable p and stats. And we are here mainly interested just in this one here. And it has two values. It's 0.0077 and the other one is 4.8848. Okay, that's basically the parameters of our model. Okay, and our model is erosion rates. Let's write those. Modeled equals still B1 plus B2 times our KSN values. Okay, it's still a linear model, but just that we don't fit the least squares in the average, or the average via least squares, but fit the median. And so B1 and B2, that's basically in P, let me see, this is P2. So you see it has a value of 4.8, so that's somewhere here. And P1 is the gradient. Okay, hold on, let's plot that one. And the modeled ones. Okay, and however, it seems like also, of course, this model doesn't really capture the entire variability along our data. We could also say, okay, now let's also calculate like the lower and the upper quantile. Let's do this again. (0.1). How did I do? Ah, here. Just doing exactly the same again. Okay, this doesn't look nice. We could do that, of course, better and draw real lines. But it just shows us that in all cases, we have an increase of the erosion rate with increasing KSN. But when we can also model using the quantile regression, the variability quite nicely. Okay, we see there is a lot of variability in the end. Okay, and having I would have expected it now to be more like this, showing the problem that the variability increases to the right-hand side. But what we can do at least is, we get some predictions based on that, but we can also say something about the variability of these predictions. And actually, it doesn't get much better than that, because the method of measuring denudation rates using 10 beryllium has its own analytical problems. And in fact, we all know that, well, erosion rates, there are a lot of other factors that play a big role. Over different timescales, there were glaciation and stuff like this that probably determine the erosion rates to some different degree. And so this, however, would provide a method where you are statistically quite sound, where you cannot be, or any reviewer would say, no, or couldn't say that is the wrong statistical technique. quantile regression is super flexible in that case with a minimum of assumptions. And what you're doing is basically describing the data with a model then also accounting for the uncertainty in the model and the data. Yeah. So I know the rest of this was probably a bit, I don't know whether it was very difficult, but at least I guess there was a lot of new stuff, I guess, that you heard here. And I guess we better leave it here at that point, otherwise it's getting quite late. But before we stop, are there any questions or anything that was now, in particular at the end, was very difficult to understand? Yes. I will do that now. Yeah. And I think we stopped where, let's see whether I have, this one is here, and we stopped where we had calculated KSN. And so now I'm going to start here to there. So you'll find everything here. Calculating drainage basin stats, using scatter to look at those plots, and then finally using quantile regression to make the plots. I would recommend to you that you go carefully through these codes once again, make your own notes, because you probably, or everyone would quickly forget what one has done here. So it might make sense just to store that code and bring in your own comments so that you know in 1 month or so when you might look at it again what you have actually done here. And the good thing is now you have a code that just takes the data at the beginning and processes everything, and as such you have a very reproducible document or approach. Just everything is stored in that document. And you could probably apply it in similar ways to other data as well. Okay, with that, I would leave it here. Thanks again for following this course. It was a bit quick at the end. I hope it nevertheless conveyed some of the important stuff that you can do with TopoToolbox, and happy to take questions or anything, whatever. Yeah. Good, thanks.